glycolysis. And in this first reaction, we're already doing an energy investment. So we're going to consume 1 molecule of ATP to phosphorylate glucose to make glucose 6-phosphate and then ADP. Now, the reason why this is so important is first of all, it's gonna this first reaction is gonna basically set up all of the other reactions for glycolysis. But the other thing is that it's a way to sort of tell the cell, okay, there's glucose all over in the cell. It's free floating. It's stored in different granules. But we want to dedicate this glucose molecule to metabolism. We're going to metabolize it. So by phosphorylating the glucose, it's sort of a way to say, okay, this glucose molecule, now we're going to use it. And so that's also the purpose of why glucose becomes phosphorylated. So the second step of the reaction is it's an isomerization reaction. And the enzyme that catalyzes this reaction is called phosphoglucoisomerase. Also known as phosphohexoisomerase. So this isn't going to use any ATP at all, so we're still at -1 ATP. And in this reaction, we have glucose 6-phosphate. It is linearized into the linear form, and glucose 6-phosphate is going to become isomerized. So instead of, so we have at carbons 1 and 2, a C double bond O and an OH group. Those groups are going to be switched. It's going to undergo an isomerization reaction. So then our product is on the first carbon, we have COH, H2, and then the second carbon is C double bond O to make fructose 6-phosphate. Which then can be cyclized back into the cyclic structure again. The next step is another phosphorylation reaction. So we're going to use another molecule of ATP. So now we're going to be at -2 ATP. It's going to be a phosphorylation. Generally known as a group transfer. And the enzyme that catalyzes this reaction is phosphofructokinase. And it makes a lot of sense because the substrate, right, is a fructose 6-phosphate, so it's like a phosphofructose. So we have fructose 6-phosphate. It's going to react with ATP in a phosphoryl transfer reaction, where one of the phosphates are going to be transferred to the first carbon of fructose 6-phosphate. So it's going to attach a phosphate to this alcohol group to make fructose 1,6-bisphosphate. The bis means there's 2 phosphates there. Now, and then also ADP. Now, sort of the goal here was to make fructose 1,6-bisphosphate. Why did we need to hydrolyze ATP? Why was that necessary to do so? Yes, Ryan.
To piggyback reactions because it is unfavorable to the bond.
Exactly, that's exactly it. So which bond was being made?
I always mix this up.
So we have a attachment of an alcohol and a phosphate group. That would be what type of bond? It would be a phosphoester. Yeah. Yep, it's a phosphoester bond. So we made a phosphoester bond, which remember that is approximately, positive 15 kilojoules. And these are just approximate numbers. And hydrolysis of a phosphoanhydride bond in ATP is negative 30 kilojoules per mole. So we needed to hydrolyze that ATP in order to sort of pay for that bond that was being made. So this step in glycolysis, this is also an irreversible step. And this is also called the committed step of glycolysis. What that means is once glucose reaches this stage, reaction number 3, once we make fructose 1,6-bisphosphate, now that molecule, glucose, is now destined to go through all of glycolysis. Previous to that, reaction number 1, when we make glucose to glucose 6-phosphate, glucose 6-phosphate can actually be made into other things. But at this step, now we have to keep going. All right. So the next reaction doesn't require ATP. We still have -2 ATP. The next reaction is, it's an aldyl cleavage reaction. And it's going to fall under basically just the general type of reaction, which is non-hydrolytic cleavage. The enzyme that catalyzes this reaction is aldolase, because the enzyme is cleaving an aldo. So we can see this is fructose 1,6-phosphate, and this group here, so the C double bond O followed by carbon, followed by another OH, that is an aldo group. And so what aldolase does is it breaks the carbon-carbon bond right here. So it breaks that bond between carbon number 3 and carbon number 4. So when it breaks that bond, it makes 2 products. It makes this product called dihydroxyacetone phosphate. I'll write that out. Also known as DHAP for short, because it's such a long word. So this is sort of the upper half of the molecule. So this is a ketose. And then the second part of fructose 1,6-bisphosphate becomes converted to this molecule, which is called glyceraldehyde 3-phosphate. So this has an aldehyde group on it, and so it's an aldose. And we're actually going to go over the reaction mechanism of this enzyme so you can see why we actually made these 2 products. So just to orient you, for DHAP, we're going to call this carbon number 1, 2, and 3. And then for glyceraldehyde 3-phosphate, we're going to call this carbon 1, 2, and 3. Okay, so at this point, we formed 1 molecule of glyceraldehyde 3-phosphate and 1 molecule of DHAP. The next step is then to do an isomerization, which is then going to convert DHAP into glyceraldehyde 3-phosphate, so into another molecule of glyceraldehyde 3-phosphate. So we're still at -2 ATPs. this is going to be an isomerization reaction. The enzyme that catalyzes this reaction is called triose phosphate isomerase. And so what it does is it's going to take DHAP, here's carbon 1, 2, and 3, and it's just going to switch the OH group and the double bonded oxygen, and it's going to switch them between the two carbons. So that means that carbon number 1 will have an aldehyde, and at carbon number 2, we have an alcohol there. So that makes our second molecule of glyceraldehyde 3-phosphate. So basically, reactions 1 through 5, overall you're trying to take glucose, so one molecule of glucose, and convert it into 2 molecules of glyceraldehyde 3-phosphates. So that's kind of what reactions 1 through 5 was about. And remember, this was our investment phase. We had to burn through 2 ATPs to get to this step. Now, reactions 6 through 10, we're going to take 2 molecules of glyceraldehyde 3-phosphates and convert it into pyruvate. So what that means is that since we have 2 molecules going through reaction 6 through 10, 6 through 10 is going to happen twice, right? For each molecule of glucose that goes through glycolysis. Okay, so now we're going to start reaction 6. We're going to this is now going to be sort of going into the payoff phase. In this reaction, which does not require any ATP, so it's minus 2 ATP. This reaction is going to be an oxidation reduction reaction. That's also accompanied with phosphorylation. And the enzyme that catalyzes this reaction is called glyceraldehyde 3-phosphate dehydrogenase. So anytime there's ever a reaction that involves oxidation reduction, usually, not always, but usually the enzyme name has dehydrogenase attached to it. Okay, so in this reaction, we have glyceraldehyde 3-phosphate. So here is carbon number 1, 2, and 3. I'll zoom in a little bit closer. So we have this aldehyde group. It's going to become oxidized into essentially the equivalent of a carboxylic acid. And so NAD is going to act as the oxidizing agent and accept a pair of electrons from glyceraldehyde 3-phosphate. So glyceraldehyde 3-phosphate becomes oxidized, and then it also becomes phosphorylated. So an inorganic phosphate comes in, and it forms a bond with glyceraldehyde with the oxygen of glyceraldehyde 3-phosphate. To make this molecule called 1,3-bisphosphoglycerate. We call it 1,3-bisphosphoglycerate because there's a phosphate or a phosphor group attached to carbons 1, 2, and 3. And then the 8 indicates there's like a carboxyl group there, or a carboxyl group. So here, even though this not really carboxyl group, if you hydrolyze it, you can imagine that would be a carboxylate group. Okay, and so this is reaction 6. So at this point, how many NADHs have we made from one molecule of glucose? Right, two NADHs, because there was actually 2 molecules of glyceraldehyde 3-phosphates that became oxidized and phosphorylated. So there's actually 2 NADHs that were produced at this point in glycolysis. Now, what is significant about this step? What happened when we made 1,3-bisphosphoglycerate? What was that? It did come from somewhere else. So it didn't come from ATP, right? So this actually consumed no ATP because it's actually coming from like phosphate in the solvent. But we made 1,3-bisphosphoglycerate. What's significant about this molecule? Yes.
Are there high energy bonds in it?
There is, yep, there are high energy bonds. Can you see which high energy bond that we made?
Enol phosphate.
It's not quite an enol phosphate. A what? It is a mixed anhydride, or it's also an acyl phosphate. Same thing, right? We made an acyl phosphate here. And if we remember, this acyl phosphate bond, right? This is a really high energy bond. If we break this bond, it releases a lot of energy, something like negative 50 kilojoules per mole. So now that we made this high energy bond, we are going to immediately cash in that bond to make some ATP. So that's the next reaction, is we're going to hydrolyze that. We're going to couple the hydrolysis of the acyl phosphate bond in order to make ATP using the bond energy of hydrolysis. We're at reaction number 7. This reaction is substrate level phosphorylation. This means we're making ATP here, right? By directly phosphorylating ADP at this enzymatic step. So this is an example of a group transfer reaction. And the enzyme that catalyzes this reaction is called phosphoglycerate kinase. So here's our 1,3-bisphosphoglycerate with its high energy bond. It's going to react with ADP, and this phosphoro group is going to be transferred to ADP. So we're going to make ATP. So we're actually making a phosphoanhydride bond. And then our product here is 3-phosphoglycerate. So we had a acyl phosphate. Remember, that's a high energy bond. We broke that bond to then transfer this phosphate to ADP to make ATP. Right? We coupled those 2 processes of making a phosphoanhydride bond and breaking an acyl phosphate bond to then make ATP. So before, we were at negative 2 ATPs, and now that we've made ATP here, where are we at in terms of ATP tally? 0 ATPs, that's correct. Okay, so the next few steps are going to be more preparatory steps to make another high energy bond. So the next reaction, we have an isomerization reaction. 0 ATP here. The enzyme that catalyzes this reaction is phosphoglycerol mutase. So in this reaction, we have 3-phosphoglycerate. So here's carbon 1, 2, and 3. And we're simply just going to change the positions of the OH group and the phosphates. So at carbon number 1, the phosphate group is going to go here. And at carbon number 2, the phosphate goes on carbon number 2, and at carbon number 3 is where the OH group is connected. So it's just an isomerization reaction where the phosphate's now transferred to carbon number 2. So we call this 2-phosphoglycerate. Reaction number 9 is a dehydration reaction. That's catalyzed by enolase. So it takes no ATP here. We're at 0 ATP still. In this reaction, a molecule of water is going to be removed from carbons number 2 and 3 to go from a single bonded carbon to a double bonded carbon. So this gives us phosphoenophosphate as the product. Also known as PEP. And what have we made now? Yes. Mm-hmm. Sorry, phosphoenolpyruvate. I messed that up. Good catch. Would have really messed that one up. Okay, phosphoenolpyruvate. I wrote that wrong on my notes. Okay, so now what's significant about this molecule? It's an enophosphate, right? So here's our enophosphate. So what do you think we're going to do with that enophosphate? Mm-hmm. So we're going to break the bond and... What was that? It will tautomerize. That's part of it. Justin?
Oh, I can create more ATP.
Exactly, we're going to create more ATP. We have a high energy bond, so we can use that to make ATP out of it. So PEP, so phosphoenolpyruvate. Actually, let me just write the reaction first. So this is going to be substrate level phosphorylation. The enzyme that catalyzes this reaction is pyruvate kinase. And this is an irreversible reaction. Okay, so PEP is, we're going to hydrolyze that bond. We're going to break that bond. And that phosphate group, that phosphoro group, is going to be transferred to ADP to make ATP. So we're going to make, from this step, coming from one glucose molecule that went through this all the way to this step, we're going to make 2 ATP from this step. So we're at positive 2 ATP. So we'll make 2 ATP, and then as a product, it forms enolpyruvate, which then can tautomerize to make ketopyruvate. And we just simply call this molecule pyruvate. So that's the last step in glycolysis. We went through all 10 reactions. I went through every single enzyme because I want you guys to have at least heard them all once in your biochemistry careers. But there's only 3 enzymes that you guys need to actually remember the names of in glycolysis. And these are the enzymes that are involved in the irreversible step. So the first is hexokinase, which is the enzyme that converts glucose to glucose 6-phosphate. The second is phosphofructokinase, so I'm just going to write PFK for short, which converts fructose 6-phosphate to fructose 1,6-bisphosphate. And then pyruvate kinase, which is the enzyme that converts phosphoenolpyruvate to pyruvate. So those are the enzymes that you need to know for glycolysis. All the others, I will love it if you just happen to decide on your own to know them, but these are the minimal ones. Okay, so the control points of glycolysis also happens to be occur at the irreversible steps. So there's just times where we need to either speed up or increase glycolysis, and we can do that. So we can control glycolysis, and we can do this by basically allosteric regulators. So hexokinase is allosterically regulated by glucose 6-phosphate. So if there's too much glucose 6-phosphate around, which could be the case if you have a really, really high rate of glycolysis, right, then that glucose 6-phosphate can inhibit the enzyme. So it can act as an allosteric inhibitor. Why do you think it would be important to regulate the enzyme at this step? Why would that make a lot of sense? Yes, I'll.
It takes energy to read the glucose 6-phosphate. If you have a lot of it, you don't have to waste energy.
Yeah, that is a great reason. Yep, so that's a good reason. Is there another reason you guys can think of? Haley?
You have not committed at this point yet to making the pyruvate. I think it's like step 3 is when you committed. But at this point you're not, so you can still go backwards.
You could still use the glucose 6-phosphate for something else.
Yeah, yep. The thing I was thinking of was that, right, it's a lot easier to try to regulate something at the beginning of the pathway than at the bottom of the pathway. Like, let's just say, you like fell off a waterfall, right? It's really hard to stop falling at the end of a waterfall, and it's much easier to sort of prevent it from happening when you're at the top of the waterfall. So phosphofructokinase is also an enzyme that's regulated. ATP is an allosteric inhibitor, and ADP is an allosteric activator. And there's a very important rationale for this. So the levels of ATP and ADP, it's sort of a energy sensor for the cell. So if there's high levels of ATP in the cell, and there's low levels of ADP in the cell, this means that the energy is high. There's plenty of energy around. We don't need to keep making more ATP when we have plenty of it on hand. So if there's plenty of ATP around, we don't need to continue doing glycolysis. It's going to feed back on phosphofructokinase to inhibit it. And so the opposite is true, that if there's low ATP and high ADP, that is an indicator that the energy status is low, and that we need to make ATP. We need to, run glycolysis faster. So we need to increase the rate of glycolysis. So that's going to activate the enzyme, which will then make the pathway go faster. And then the last step, pyruvate kinase, is ATP is an allosteric inhibitor. Okay, So the overall pathway in glycolysis, I'm going to summarize it, is glucose, which is 6 carbons. It got broken down to 2 pyruvate molecules. So those are three carbons. 2 NADHs became reduced to 2 NADH plus H plus. Remember that in steps 1 through 5, we used 2 ATPs. So I'm looking at this and I'm trying to, okay, so two ATPs were consumed for steps 1 through 5. And then steps 6 through 10, 2 ADPs were reacted with 2 phosphates to make 4 ATPs. So if we add all of these reactions together, we can cancel out 2 ADPs on this side and then 2 ADPs on this side. So we have 2 ADPs here, and then 2 ATPs here, and 2 ATPs here. So our net reaction is glucose plus 2 phosphates plus 2 ADPs plus 2 NAD plus gives 2 pyruvates plus 2 ATPs plus 2 NADH plus 2 H pluses. Oh, and then the last thing I forgot to mention is that water was also produced, so plus 2 waters. So I don't expect you guys to just memorize this net reaction. I just want you to have an idea of the different, products that are made from glycolysis and where they're coming from. Okay, so let's talk about regeneration of NAD plus and fates of pyruvate. Now, in the cell, NAD plus is limiting. There's only a certain amount of NAD plus. So if we were to go, run like a mile as fast as we can, right, we're going to end up burning all of our NAD pluses. Okay, what specific step uses NAD plus in glycolysis? What was that? Yeah, so step 6, the glyceraldehyde 3-phosphate dehydrogenase, right? We use NAD in the reaction in order to carry out glycolysis. So if we run out of NAD plus, we're going to not be able to carry out glycolysis anymore. So this means that NAD plus needs to be regenerated in order for us to carry out glycolysis. So this can happen either aerobically or anaerobically. And this is going to, in the process, metabolize pyruvate. So under anaerobic conditions, pyruvate, and we're going to see this in the next few lectures, pyruvate is going to,
Anaerobic or aerobic?
for aerobic.
Okay.
Yep, so for under aerobic conditions, pyruvate will be converted to acetyl-CoA, which will then be oxidized to CO2. And then this is going, and then the NADH, it's going to be regenerated by oxidizing it through the electron transport chain. So NADH plus H plus will react with oxygen to make water and NAD plus. So as long as there's oxygen around, we can regenerate NAD plus by oxidizing it through the electron transport chain, which is in the mitochondria. And we'll learn the specific steps of how that happens when we go over oxidative or the electron transport chain. However, it occurs a little bit differently under anaerobic conditions. So under anaerobic conditions, this means that NAD plus is going to be regenerated without O2, without oxygen. And so we call this process fermentation. And so the way this works is in humans, pyruvate is converted to lactic acid. So humans, here's pyruvate. Pyruvate is going to act as an oxidizing agent and oxidize NADH back to NAD+. And in doing so, pyruvate is going to become reduced. So this C double bond O is going to be reduced to an alcohol to make lactate. So that's why when you go for a really vigorous sprint, that's why you make lactic acid in your muscles, because your body is trying to regenerate NAD in order to be able to continue carrying out glycolysis. In yeast, it happens in a different way in that we can make alcohol from it. So this is the process by which beer is made. So pyruvate it first undergoes a decarboxylation, so CO2 is lost. This requires a cofactor called TPP, and it's catalyzed by pyruvate decarboxylase. So then, after the decarboxylation, we make acetaldehyde. And now that acetaldehyde is produced, it's going to act as the oxidizing agent to oxidize NADH back to NAD plus again. And in the process, acetaldehyde itself is going to be reduced to make ethanol or alcohol. So this enzyme that catalyzes this reaction is called alcohol or ethanol dehydrogenase. And this enzyme that catalyzes this reaction is lactate dehydrogenase. Okay, so this is why when, right, in the process of making beer, this is where the carbonation comes from, right, the CO2 that's produced from the decarboxylation of pyruvate. Any questions up to this point, Sarah?
When you're transitioning it from acetaldehyde to alcohol, is alcohol what?
Oh, I wrote dehase, but it's short for dehydrogenase. Any other questions? Yes.
I have a question. So
Yeah.
if you're undergoing a lot of anaerobic activities, does that mean that your body's creating a lot of lactase dehydrogenase so that way you can create even more NAD plus?
So So remember that enzymes, they're always regenerated. So no, you already have, the enzyme is already there, but what happens is there's more pyruvate around. So you have glycolysis. So glucose is being converted to pyruvate. So there's more pyruvate around, as well as more NADH, and so there's going to be more, basically, substrates that are going to then be converted to lactic acid by the enzyme. But there's not any more of the enzyme around. It's just there's more substrates around for the enzyme to actually act upon. Yeah, good question. Any other question? Yes.
So for the fermentation,
Uh-huh.
so it starts with starch, is that right? Some kind of starch? Don't we put like some starch in the yeast?
Yeah, I believe that there is some type of starch, which probably, I'm sure there's glucose that's in there,
Okay.
which then that glucose is what gets, fermented. So it's going to undergo glycolysis and then,
So it does do glycolysis then?
Yep,
As part of the end?
yep, exactly, yes. So when glucose goes through this pathway, where it undergoes fermentation, we call it anaerobic glycolysis. Okay, so I was actually going to go over a reaction mechanism, but I think in the interest of time, and in fact we went over a lot of information and we're in the last few minutes of class, I'm not going to go over it today, and I'm just going to go over one reaction mechanism next week. So I'm just going to talk about this really quick. So this last page is just a table of the actual delta G naught primes and delta G's of each reaction. So the pathway as a whole, if you add it together, is favorable. Some steps are unfavorable. And flux through the entire pathway pulls everything along. And you can see that, right, all of the reactions, the delta G's are, they're small, except for reactions 1, 3, and 10. Those are large and negative. So those are the irreversible reactions. Before we leave, I want to share with you guys a video for those of you who find music to be a good way of learning. So this, hold on, let me just do something really quick.